Hey everybody, so today we're back with a new series. We have completed that OPSEC Harden Your Box series where I go through, show you guys how to tighten up your machine. Well, now we're going to start talking about malware. If malware does get on a system, what does it do? How does it function? How do you detect it? How do you get rid of it? And various methods of just various things malware does. Okay, so this is going to be it's going to be theory heavy. Okay, up front, I'm going to do a very in-depth lab at the end of this, but there are some essential things that we have to cover up front so that those of you who aren't pros at this know what's going on. Okay, now the lab here is going to, so I've written it's not malware, but it behaves like it. Basically, it goes right up to that line of exploitation, right? And so the lab is going to focus on this custom malware that I wrote, and then we're going to go through and see what it's doing, how to detect it, and what it does to a system. The focus of this is going to be on hidden files. Okay, so that's really the topic of this video, is hidden files and how malware uses hidden files to hide. Okay, and this is going to be a Linux focused tutorial. Okay, but we do need to talk about Windows. All right, that's why you see here in the notes we're going to talk about Windows first. Okay, because Windows and Linux, hidden files operate completely differently. They're completely different. Okay, and most people, they grow up using Windows, right? That's what they think of when they think hidden files, right? They think about going into Explorer, enabling hidden files, and seeing them. People that even do that, okay? And so, I want to set the groundwork for, if you are coming from that Windows world, how different it is, okay? So, let's dig in. Okay, so, the Windows mental model. Okay, so on Windows systems, hidden files, they're not a trick or a convention like they are on Linux, right? They're explicitly marked as hidden at the file system level. Okay, and that means when a file is created on an NTFS file system, it can be assigned, hidden, system, read-only, archive, things like that. And so these attributes are stored directly in file system metadata. Okay, they're not cosmetic; they're real flags that the OS understands and enforces. And when a file is marked hidden, the OS actively participates in concealing it, right? Like, basically, it's kind of the file system tricking itself into not seeing these files, okay? Now, when a file is marked hidden on Windows, File Explorer, it won't show up by default. A lot of Windows APIs, they won't return it unless you specifically tell it to. GUI tools inherit that behavior automatically, and even command line tools may suppress unless you specifically use flags to not suppress the hidden files. And so, like I said, right, it's like the OS basically lies to itself on behalf of the file unless the user explicitly says, show me this thing. So, so this is the main distinction on Windows. Okay, so on Windows, the file system and the OS collaborate to decide what the user is allowed to actually see by default. Now, so I'm going to pull up Windows here, right? So if we go into Windows, and we go into the local disk, and then we go into users. And then we go into our username, and then we enable hidden files, right? So we come in here, we say hidden files, and a big one is app data, right? So this directory is very deep. Okay, so if you go into here, like, you can get pretty crazy. So if you go into roaming, you go to Microsoft, you go to Windows, you go to Start menu, you go to Programs, you go to Startup, right? I mean, look how deep that is, okay? Now, notice the last directory here that we went into, Startup, right? anything placed in this directory will be executed when the user logs in. But at interactive session start, right? We're not talking about like boot up. Okay, we're talking about after you actually get in here and you start interacting with Windows. And Windows Explorer enumerates this folder and launches its contents. And so, files on Windows, there's exe files, there's back files, cmd files, ps1 files. You have to do some execution policy caveats to get ps1 files to launch. And then a big one that I used to use when I was misbehaving was LNK, right? That's shortcuts pointing to anything runnable, okay? That was a trick that I used to do. Now, theoretically, this is a good spot for malware to hide because it's deeply buried, user contextual, and because, right, we went into a user's directory here, it's user contextual. And the execution is implicit, right? You don't need to click on anything, okay? App data is that folder's hidden by default. There's a long path, which means that it's not going to casually be discovered. There's really no admin rights required. It survives reboot. There's no registry keys involved, no services, no scheduled tasks. And it even works under lockdown systems. Now, the reason that I say that it's theoretically is because it's well known, right? It's just a well-known it's a well-known directory. So if you are actually trying to get away with something, it's probably nowadays it's probably not the best place. But a great example of these, on Windows, how there are these kind of inherently deeply nested directories, okay? And now, so down here I show the persistence type, where it lives, and why it's persistent in Windows. Okay, so registry run keys, schedule tasks, services, and WMI and COM. Right, so these are the big ones. Right, these are usually what are exploited on Windows for malware. Okay, now why does this matter for attacking? Because hiding is enforced by the OS, okay? Attackers on Windows don't really need to rely on human laziness alone because, you can rely on default system behavior. And historically, Windows malware has abused this, okay? So, marking files as hidden and system so they don't appear in Explorer. Dropping payloads into directories that users rarely browse manually, like with a dropper or something, which we'll get to in the lab. Relying on the fact that most users never enable show hidden files because it clutters up your experience, right? And then using registry keys that don't surface unless they're explicitly inspected. Now, here's a little story, right? So whenever I was misbehaving on a Windows machine, I often thought if I set the right attributes, basically the OS itself is going to help me stay invisible. And so this is what's called enforced hiding, okay? So now, obviously, right, the Explorer defaults, they're a security liability. Okay, so by default, Windows Explorer, it doesn't show hidden files, it doesn't show system files, and actively warns against enabling those views. So this should stand out to you as a dangerous assumption, right? So, if I don't see it, it's not there. And that's the assumption that attackers make. I've seen moderately technical users often forget to enable hidden file viewing and assume that, I guess, Explorers is view as authoritative, and that's what attackers want. They want you to think that. Okay, so let's get into some ways that Windows does this. Okay, so registry persistence is a big one, right? So this is hiding without having to actually put any files on the system. This persists data through, the big one is registry run keys, right? So Windows has specific registry locations that tell the OS when a user logs in, run this program. Attackers commonly focus on these user-level auto-run keys and system-wide auto-run keys. These keys are designed for updaters, background utilities, and startup applications. And attackers like these because there's no file. You don't have to click anything, right? Execution happens automatically, and it's often invisible to users. It survives reboots and can point to hidden files or benign-looking binaries. And if Windows itself launches something at login, it tends to look legitimate. It tends to look legitimate to users, right? It's like, well, it's a Windows thing, right? They'll look at their task manager and they may see something in there, but if the process is properly named, they're just going to be like, oh, that's just Windows doing a Windows thing, okay? And then, of course, scheduled tasks. That's pretty obvious. Now, Service Control Manager. This is a big one, right? So the Service Control Manager is what manages these long-running background processes on Windows, right? Windows services. Attackers like these because services can start at boot, services can run as system, and services don't require any interaction. And most systems are running hundreds of these, so it's very easy to kind of disappear in the mix, okay? And then you have COM objects and WMI subs. Now, COM objects, what these are, is they allowed code execution using Windows component architecture. And WMI subs allow actions to trigger automatically on system events. So these execute without any obvious file. They can trigger on system changes, and they persist deeply within the OS internal. And so attackers like these because they have very low visibility, they're very rarely audited, and they're difficult to understand unless you know what you're doing, okay? And they survive reboot, the big one. And so from a defender's perspective, they will see something executing, but there will be no file. And so this confusion, is intentional. And so a lot of these don't correspond, and like I keep saying, right, these do not correspond to obvious files. They don't show up in Explorer. They require tools to inspect. And on Windows, not seeing a file doesn't mean that it's not running, okay? The OS kind of encourages this illusion. Now, typically with defenders, right, on the defense, you should always assume default visibility is untrustworthy, right? So common defense techniques are enabling those hidden files, using tools to enumerate hidden attributes. So what those tools do is they bypass Explorer's default behavior and they reveal files the OS tries to hide. System protected artifacts and suspicious binaries placed in trusted locations. Okay. Now, and then also scanning NTFS metadata directly. So if hiding is implemented at the file system level, you have to operate at that level as well. And then, of course, auditing, right? That's a big one. Auditing registry auto-run locations. So this allows defenders to see who holds the OS to execute something automatically. This allows defenders to see who told the OS to execute something automatically. And on Windows, persistence lives outside the file system. So you can delete every suspicious file on your machine, and the malware could still be there, right? If the auto run still is intact. And then, using sysinternal tools like auto run, process explorer, things like that. So Windows defense begins with overriding the OS's attempt to be helpful. So the key lesson here is on Windows, hiding is a feature of the OS, okay? On Linux, hiding is like a habit, right? And this difference is why Linux attackers use Dotfiles, path tricks, and behavioral camouflage instead of file system flags, which, we're going to show coming up. Now, like I said, the reason that I wanted to discuss Windows here is because I think most people subconsciously assume that hidden means hidden by the operating system. And visibility is like a security control, and these file managers, you can just rely on them. Right? You don't have to question them. And those assumptions are all wrong on Linux, and attackers exploit that gap. So if you don't unlearn this Windows model first, everything that we're going to go over here is going to feel kind of weird, right? And so here's a side-by-side model of this stuff, right? So on Windows, hidden is an attribute. On Linux, it's a naming habit. Right? And then here on Windows, the file system knows what's hidden and the OS enforces that invisibility. On Linux, the file system doesn't care. okay, and the OS does nothing special. Um, and then, we have attackers relying on, right? So they're very different. You can see how these are all very different across the board. And so that's why I wanted to go into this Windows stuff first, to show, to kind of get you, if you are from the Windows world, to make you realize that this Linux stuff, it doesn't operate the same way. Okay? Now, in Linux world, we have convention-based hiding. Okay? On Linux, there's no such thing as a hidden file at the file system level, right? There's no hidden attribute, there's no system flag, there's no kernel enforced invisibility, there's no metadata that's telling the operating system to not show this, right? A file is considered hidden on Linux for one reason. Its file name starts with a dot, okay? That's it. This is not security or enforcement, it's really a social convention. As you see here on Windows, you have a hidden attribute, the OS hides the files, and then the user doesn't see anything. On Linux, it's a naming convention, a .file. Tools hide it by default, like ls. The kernel still returns the entries because there is going to be a process going, right, which we'll get to. Now, where does this come from? Like, why this .file thing, right? So dot files were originally intended in Unix to kind of declutter your UI. It was to keep kind of configuration files out of the way and working directories easier to read. And like I said, to reduce that visual clutter. .profile, .bashrc, .vimrc. Like if you look at a home directory in Linux, right? If you look at a home directory, like, dude, it's crazy, right? It's wild. Like, you got all kinds of stuff in here, right? Like, you can clean this up, obviously, but you get a lot of these dot files. And you can see the difference, right? So here, what I did was I ran lsla. If I just run ls, right, like, it's a lot easier to read. And then you could just do lsl and to get the list. And yeah, it declutters it a lot. And this is what attackers rely on. They rely on these noisy directories. And similarly to Windows, they rely on you not going to certain places, you being a casual user and you not looking at things. Like, that's what it's really about. Now, no one really designed a mechanism for secrecy, right? It's not about that, obviously. It predates modern threat. Sorry, not thread. It predates modern threat models by decades, right? There was never any rule to hide this from attackers, right? The rule was don't distract humans. And of course, attackers notice that. So what does the kernel actually do? So the kernel stores file names exactly as given, and it does not treat the dot specially, really. It returns dot files to system calls normally, and it makes no attempt to hide anything. If a program asks the kernel to list files in a directory, the kernel replies with them all. The tool, right? It is about the tool that decides what to show, right? Like I just showed. LS is a liar, man. Like, LS, it hides dot files by default. And like I said, this was a UI decision, not a security decision. Because, LS hides dot files, and like I showed, ls-a, it shows everything, right? Nothing here is changing at the OS level. Only the presentation changes, right? So this leads to this dangerous habit, right? If I don't see it, it probably is not there. It's the wrong idea to have on Linux, okay? And so convention-based hiding is liked by attackers because it depends on human behavior. And so a Linux attacker thinks like, well, you're not going to use ls-a everywhere, right? Dot files kind of naturally blend into Linux massive config directories. And also, if you're using your home directory as a dumping ground, you're going to have a lot of shit there. And so people, and then the terms like cache and config, people sort of mentally whitelist those directories. And security tools often inherit default filters. So here, we don't hide from the OS, right? We hide from attention. And by us, I mean like attackers, right? So let's do this. Okay, so I'm going to go into, I created a little test directory here. Don't remember what I called it. Don't remember what I called it. Maybe I deleted it. Let's create a new one. So we're going to create a new directory. We'll call it demo. Demo. Nope. Come on now. There. All right. Now, okay, so I'm going to touch visible.txt, and then I'm going to do hidden.txt. Okay? Now, obviously, if I do ls, I just get visible. If I do lsa, I get both. Now, this is important. Okay? So, if I run rm, rf, and I want to delete the entire directory, sure you want to delete the only file, right? The .file is still there. Okay, now don't do this. Don't do this, guys. So sometimes this won't blow up your directory, but this has the possibility of deleting your ... Okay, and it's going to ruin your day. So what is happening here is star or asterisk, it doesn't match .files. The shell never actually passes .hidden.txt to RM. Okay, therefore RM doesn't even know that it's existed. The tool just doesn't do that. And so it's important to understand that this is a shell behavior, not a file system one. Okay, so what are you supposed to do, right? So if you're running bash, you can use shop-t. I'm running ZSH, and its equivalent is set opt, right? So what you can do is you can come over here and you can run set opt glob dots, and then what you can do is when you go in and do this, right, boom, and it's gone. So that's one way that you can do it. So .files are camo, right? They're not invisibility. So on Linux, like I said, .files are not invisible. They're boring. They look normal, and they don't trigger urgency. Right? So a directory like, your user home.config, this could contain hundreds of files, right? Nested subdirectories, frequent legitimate changes, and dropping a malicious file there, it doesn't make it hidden, it makes it forgettable, all right? And so another important thing is Linux persistence is not attribute based. Okay, so what does this mean? Well, unlike Windows, Linux attackers, they can't rely on the operating system to hide things, right? We have to rely on placement, naming, timing, and behavior. So, on Linux, you're typically dealing with, for persistence, you're dealing with .file executables and user directories, scripts sourced by shell startup files, abuse of scheduled jobs, that's a big one, long-running background processes, and services that look legitimate. Personally, these were my favorites, the scheduling jobs and the services that look legitimate. And that's kind of what I did with the fake malware that I created for the lab. You should see the difference here, right? So there's no hidden flags, there's no system attributes, there's no OS enforced concealment. Everything is visible if you look. Attackers don't mark hidden files in Linux, they kind of exploit your expectations, okay? So, for defenders. Now, on Linux, defense begins with the assumption that the default output in your UI tools is incomplete by design, which they are. So as a Linux defender, I have a habit, guys. I don't do ls. This is muscle memory. This is what I do every time I list a file. Even if I'm just casually using Linux, I always do lsla when I list a directory. And then you can enumerate explicitly with find, which we're going to talk about. You cross-check directories, you correlate file systems with the proc directory, and treat nothing found as a question, not an answer. Okay? So let's talk about proc. Okay? The reason that proc matters more on Linux than Windows is because Linux does not hide processes, right? Once a program is running, it has a PID, it has an executable path, it has open file descriptors, and it appears in proc, okay? So there's no naming trick can erase that, All right, so you can hide files from humans, you cannot hide processes from the kernel. And so I'll be emphasizing proc heavily here in this lesson. All right, so you see here, your userland tools, that's a blind spot, right? They're filtered by convention, they may miss hidden files. The kernel view, proc and auditd, those show true execution details. And then the processes are reality, right? Your UI is not reality, your files are not your reality, it's your processes that are reality on Linux. So Linux hiding is psychological, it's not technical. Linux hiding works because humans stop looking, not because the OS blocks them. And so, you rely on visual fatigue, that familiar clutter, and then assumptions about what normal directories and normal binaries are called. And so, you counter this by enumerating everything, questioning silence, correlation behavior, and trusting the kernel over the UI, right? So, Dotfile naming, UI hides by default, humans ignore it, attention fatigue, but the kernel always returns it, right? There's no hidden attribute. Now, the executable bit. This is really all that matters on Linux. On Windows, you got to have a file extension. exe, bat, cmd, something, right? On Linux, though, file extensions don't really have any meaning to the operating system. They're just naming conventions for humans. You can rename a binary to anything. You can rename a binary to notes.txt, a script to .config, or a config file to .exe. Linux doesn't care. The kernel never asks if a file ends with a particular extension. All right, so here you'll see you have an attempt execution. The only thing that the OS is checking is if the execution bit is set. If it's no, the permission is denied. If it's yes, it checks if it's a valid elf, which we'll talk about. If it does, it loads and executes. No, it checks for a shebang. All right, and we'll talk about shebang here in a second. This defines a script, right? And so then, if that script is, if that shebang is defined, it invokes that interpreter, right? That's what that shebang script at the head of like Python and bash scripts do. That basically tells the operating system what interpreter to use. And so if it has a shebang, it's going to invoke that interpreter. If it doesn't, you get an execution failure, right? So when you attempt to execute a file, the kernel asks only a small number of questions, and at a high level, you're like, do you have permissions to execute? Is this file a valid executable or script? Are you invoking it directly or through an interpreter? That's pretty much it. There's no extension check. There's no file name inspection. There's no semantic meaning to attaching names. And so the execution bit, that is the ultimate gatekeeper, right? Linux permissions are represented as, RWX, read, write, execute, and the execute bit is the authority. If the execute bit's not set, the file can't be executed directly, even if it contains valid code or if it's a perfect binary. If the execute bit is set, the kernel will attempt to execute it regardless of the name or how harmless it looks. So in Linux, permissions are what matters. They matter much more than file names, right? So if I go in here and I do echo hello, and then I just create test.sh, and then I do, right, I'm going to get permission denied. But if I go in and I set that X bit, boom, right, it executes. Now, executing binaries versus scripts. So, if a file has the executable bit set and contains a valid ELF binary, the kernel loads it in the memory and transfers control to it. There's no interpreter involved there. Now, what is ELF? So ELF stands for Executable Linux Format. It's the standard binary format used by Linux for executable programs. And so when you run a program, the kernel checks and it reads the first byte of the file, okay? And then it checks for what we call a magic number. Okay, this is a fixed sequence of bytes at the beginning of a file that identifies its format. You know, and you can read through this, but the important thing in here is let's take a look at it, right? So if I go in and I do, there's a few ways to do it. I'm going to use hex dump here. If I go in and let's say I'm going to do a hex dump on ls, right there, okay, you see elf, okay, and then there's you can use od, you can use readelf, but yeah, there it is right there. So that's what Linux is checking for to make sure that a binary is a legitimate Linux binary. Now, executing a script. So if a file doesn't have a valid elf binary, it checks if a file begins with a shebang, right? Like the shebang bin bash, shebang bit, shebang binary Python 3, right? This is what specifies the interpreter, like I said. The kernel reads the shebang, launches the interpreter, and passes the script has input. And then from the kernel's perspective, both cases are executed. Both cases are execution, sorry. So a lot of people think that scripts aren't dangerous unless they run them explicitly. But on Linux, any executable file can be run if the permissions allow it. The file can, like I said, it can look like anything, which you'll see in the lab. You look at these, and so any of these, they can execute code just as easily as malware.bin, right? The difference is permissions. It's not the appearance. Linux attackers don't need clever tricks if you can control permissions. The goal is often to place a file in a usable writable binary, set the execute bit, and then invoke it directly or indirectly. Once the execute bit's set, the kernel does the rest. If an attacker can make something executable, it doesn't matter what it's called. Now, Dotfiles plus the execution bit. This is the thing. This is the high risk combination here. So with your Dotfiles, they blend into noise. They're often ignored, and they live in trusted directories. Executable files, they have authority, can run code, and they're power. They're not decoration. So you combine these together and you have a file that looks boring but can do anything you can do. You should adopt the assumption that executable Dotfiles are suspicious. Not malicious by definition, but if you see an executable Dotfile, you should definitely check it out. Linux enforces permissions, ownership, and capabilities. Like I said, it completely ignores file extensions and names and honestly your expectations. And so attackers will exploit what Linux ignores, and defenders focus on what Linux enforces. Okay, so there's some common misconceptions here, right? So I've heard people say, "But I wouldn't accidentally run a .file," And so, but the thing is, in reality, shell scripts source .files automatically. Startup processes invoke hidden scripts. Background services can execute stuff that you never click on, and schedule jobs. Right, scheduled jobs to me are the big one. So execution does not always quite require a double click. Okay, so now you should understand why a lot of these defensive practices make sense, right? Why we scan for executables in user directories, why we flag executables and dot directories, why things like AppArmor often restrict paths and not names. So if you don't know what AppArmor is, it's a mandatory access control system. There's a bunch of these. SE Linux is kind of the standard now, but AppArmor is still used. I don't like AppArmor. I find it very hard to configure. It fails a lot. SE Linux can be difficult to set up on some systems, but if you are looking, and I'm actually going to do a video on SE Linux, but if you are looking for a modern Mac solution, SE Linux is kind of the way to go, even though it can be a pain to set up on some distributions. But what they do is they basically enforce these rules regardless of user intent. It basically says even if you can do this, you're not allowed to, right? It kind of sandboxes things in. And then next we're going to talk about perm 111, why it's so powerful and why Dotfiles deserve extra attention. Now, so let's talk about it. Let's talk about perm 111. Okay, so what this does is this is how you find hidden files. Okay, like this is the way to do it. Okay, and so what the command breaks down into is this restricts results into regular files, right? We do this because we're looking for things that can execute. Directories and symlinks, they don't execute. Okay, Now your perm.111, this is the important part. So this slash match any permission bit, right? So the 111 means owner execute, group execute, other execute. And so the entire command means show me any file that is executable by someone, anybody, right? It does not care about file name, visibility, legitimacy, or who owns it, right? It cares about capability. It pairs very well with Dotfile detection. Let's go in here and see how this works. All right, so let's create some files. So we're dealing with an empty directory, all right? Double check, yep, all right. So now, I'm gonna create some files. Okay, then we're going to create test.txt. We are going to make that executable. We're going to create .hidden and make it executable. All right, now, when we do ls, right, we get test.txt back, right? That's not a concern. We can get that back whenever we want to. Looking for regular executables is not our concern. What we're looking for are hidden executables. Okay, and so to do this, what you can do is use this command, find here in this directory. You could use this to enumerate your entire system if you wanted to. And then we're looking for files, and then perm, and then name, because we're looking specifically for hidden files, right? And we get hidden back, okay? And so, as you can see, if we were to enumerate an entire system, we would get all of these dot files back, you know, and there's other filters and stuff you can do on here, and other processing you can do to narrow things down. But that's the core thing. That's the core command for finding these hidden executables. All right, now, what about this? Okay, so what if you ran PSAUX and you saw a weird process going? Okay, so what I'm going to do is I'm going to copy over sleep and just name it something different. Okay, and then I'm going to start it up, and then I'm going to put the timer on it and start in the background. Now, if you were to do PSAUX, let's see what we find, right? So right here, got this weird name. Okay, so, well, we see this weird thing that has spawned this process, but how are we supposed to figure out where it, oh, sorry. So we see it here, okay? Right here. So we have this thing, it's got this, we don't know what it is, it's an executed dot file, which is of concern. So how are we supposed to find where it is? Well, only thing you got to do is take note of the PID. And then what you can do is you can use readlink, proc, then the PID, which is 2401103-exe, right? And we see exactly the file that spawned that process, okay? So that's how you do that. All right, so yeah, let's get into this demo. All right, let's do this lab. Had to take a little break. It's a long video, but it needs to be. This detail is important. Okay, so let's talk about this lab. Okay, so in this lab, we're going to be focused on post-execution attacker behavior. We're going to assume that the attacker already has some malware up and going on the system. They've got it on there somehow, and a dropper has placed the script, has placed the binary, and it's running. Okay, because in real incidents, malware, it's not going to run from where you downloaded it, right? Because that's going to be too easy to find. So the objective of this lab is to be able to simulate how malware is placed, observe how the file system can mislead defenders, using processes to identify the true execution path, understand how attackers probe, observe auditd, see a signature-based tool fail, manually detect suspicious binaries, and correlate host behavior with C2 communications. Okay, now let me show you the malware. Okay, also guys, tomorrow I'm actually going to go through this code, because so it goes right up to the edge, right? And so like before exploitation. So you guys can take this code and you can do something with it, right? Run it in your lab, you know, go all the way through, go crazy with it, right? And so I think it's worth going through, especially if you're not familiar with malware code. like and kind of the behavior of it, this can really show you how it's done, right? So it's going to be, of course, it's going to be in Rust, right? And so this is the code I'll be walking you through. You see it has feature flags because with most malware, you use feature flags to be able to compile your binaries based on the features you need for the environment you're trying to exploit. Okay, it kind of allows you to custom tailor the binary. Okay, and there's a lot of other stuff going on. And so probably one of the big things is it's probing, it's sending JSON data, formatted data, to a C2 server. Just quickly spun up this mock this mock server in Python, and you'll see here that the probe, right? So every 20 seconds, which is a little noisy, in a real malware, I would not do it that fast. It's all about going slow and creating a minimal amount of noise, right? And so what this is doing is this is sending a JSON, formatted data to the C2 server saying, it's got the date, timestamp, PID. It's telling you what files it probed, if it was successfully opened them, and if it didn't. Then it also tells you the errors, right? So permission denied. I got one down here. The file doesn't exist. I kind of wanted to show you guys just a few different things that, that may be sent, okay? Now, so we'll go, like I said, I'm going to create another video tomorrow. I'll put it out, and we'll go through this so you guys can really understand what's going on here. Okay, so let's get to this. All right, so now, so simulating a dropper. Okay, so this just basically walks you through it to recreate this lab. This walks you through the creation of the directories I did. So this particular malware, it drops itself into, so you'll see in the home, I'm currently in the home directory, and you'll see here that the home directory has a config directory, right? So what I'm going to do is I'm going to go into that. Okay, now I'm just going to do ls. Okay, I'm not seeing anything there. What about LSA? Okay, there is a cache directory here. All right, so let's go into that. Okay. All right, so there is a hidden executable here. All right. So at this point, currently, unbeknownst to us, right, there's a process running. The kernel's recorded its execution. The malware's probe. Remember, I showed you it's probing system paths and it's beaconing to a C2 server. Okay. Now we just did all this, right, showing you, the UI, what a user would see. Now let's turn to the kernel, the real stuff. Okay, so let's see what's up here. Okay, so PAAUX grep systemd update. Okay, so there's two of them, right? We see two systemd updates. Okay, well let's see what's going on there, right? So read link.proc. We'll just do the first one. Exe deleted. Okay, well, what about the second one? Okay, that one's not been deleted. So what's up with that? Well, so this is a thing to confuse people, right? So one of the things, and sometimes like what you can do, one of the things that I used to do is I used to have a bunch of fake binaries spin up and delete them and just leave them dangling on the system, and you can, and so this is just kind of a confusion technique, right? To leave these dangling things here and there. This is a mild example of it, but you can get crazy with that technique to confuse defenders. Okay, all right. So we've got a PID now. Well, now the next logical thing is to see if it's sending anything, if it has a network communication, right? So let's use SS, which is pretty typical, and then it's this one. So I'm gonna copy this one. And okay. Okay. Nothing came back with that one. Okay, that's odd. So let's try this other one. All right, let's try else off. Okay. Maybe let's get a little bit more aggressive with SS. Okay, so give up. It's not beaconing. Wait, right? If it's beaconing, we'll set SS on a loop. And we're probably just coming in between the beacons, right? So let's try that. You know, make sure that we're just not issuing these commands between beacons. I'm going to watch the C2 server here. Okay, it just beaconed and nothing came back. It's like, okay, well, I guess it's not beaconing. Well, this is what you need to do. You need to use strace. Now, check this out. When you run strace, okay, let it go. What you're looking for is that beacon. Okay, so you got to let it sit for a minute just to see. Oh, we got something. We have something running on port 8000. Okay, well, that's helpful. Okay, so now we can do TCP dump. Boom, right? So now we see, okay, it's sending something out, right? We can see now that, okay, it's doing something. So that's a great example, man. You know, don't rely on a single tool. You got to stack this stuff just like with anything else. If one thing doesn't work, you need to run out of all your options. Don't just assume this thing isn't talking, okay? So you saw, right? So I have all of these directories set up, right? And now what I did, so say that, you know, so this fake sudoers, right, is very important. That's an important high value file of mine. And so what I did was I went in and I attached an auditd to it, a rule to it, so I can see if it's ever, if someone ever messes around with it, right? And so, so let me show you this, right? So, I'll search. Okay, there's something going on there. And then, I can't remember the command. I think it's text format. Nah. Format text. Yeah. So let's do that. A little bit easier to right. Okay. So we see here clearly unsuccessfully opened file fake sudoers using system update. Okay, so now what you can do is you can automate this, right? Your high value files, you can have a alert sent to you if something tries to access this, right? So now, okay, so another thing that you may do is like, okay, well, hell, you know, let me scan this thing and see if it's a virus, right? And so now, usually what you would do is if you found something like this in a directory, you would kind of tend to scan the entire directory to see if there's anything else in there that's funny. But we're just going to scan this cache file. Okay. Now, so we're going to do sudo clam scan r cache. Okay. Okay, well, it found something, but it said that there's no infected files, right? So what's up with that? Like, dude, it has malware behavior. Like, it's probing files over and over and over again. It's enumerating those things. It's communicating with a C2 server. Like, what's up? Well, the thing is, man, ClamAV is SIG based. Like, it's an antivirus engine, right? It's very good at, detecting if a file matches a known malicious SIG, if it resembles an analyzed malware family, or if this is a known Trojan, worm, or macro virus. It's often, ClamAV is often used in like mail gateways, file upload scanning, CI/CD pipelines, and artifact inspection. It's not designed for behavioral situations like we have. That requires a whole different type of software. ClamAV is not going to answer, why is a hidden executable running from a user directory? Why is this process probing? Why is the binary beaconing? Is this behavior usual for the post? These are defender questions. They are not antivirus questions. Honestly, guys, if you know what you're doing, antivirus is kind of a joke. Okay, there's so many ways to get around antivirus. It's kind of laughable. Even like modern antivirus, it ain't that hard to get around. Okay, so I think that's it for the lab. I hope you guys liked it. I hope you learned a little bit of something. And like I said, I'm going to post another video tomorrow where we walk through that Rust code and I kind of explain to you exactly what it's doing. But for now, that is it. If you made it this far, man, you're awesome. Props on sticking with it. I hope this information was valuable. I hope you learned something from it. I hope you learned something from tomorrow's lesson. So yeah, if you guys have any questions, hit me up. Help each other out in the comments. Ask those respectable questions to get those respectable answers. And I'll see you guys in the walkthrough. See ya.